Okay, let's unpack this. We are jumping straight into, well, the absolute foundation of building and public safety today, fire protection.
We really are. And for this deep dive, we're leaning heavily on sources like the Brandschutzfibel, the Fire Protection Primer. It's not light reading,
Yeah.
but it's crucial because it treats safety not just as, a list of things to check off, but as a single comprehensive piece of work, a Gesamtwerk, as they say.
And that initial point from the source material is, frankly, a bit unsettling. All the huge investments, the careful planning, the fancy tech.
Yeah.
It can all be totally useless because of one tiny oversight.
That's the heart of it. It's the classic tragedy of system engineering, isn't it? Imagine a perfectly rated firewall cost millions maybe, but it's basically useless if someone leaves one small hole unsealed where a cable went through.
Just one little gap.
Or maybe a crucial smoke protection door gets propped open by accident or jammed. It happens.
So that's the weak link.
Yeah.
The whole safety concept hinges on every single piece locking together perfectly, like gears in a clock.
Exactly like cogwheels. And if just one that door, that wall penetration fails, the whole barrier against fire and, just as importantly, toxic smoke just collapses.
Which is why we really have to start right at the beginning, with a basic effort to define safety through standardization. Norming.
Yeah, standardization. Sounds dry, maybe a bit bureaucratic.
A little, yeah.
But it's the bedrock. The definition in DIN 820 Part 1 is actually quite clear. It's about the systematic unification of things, physical things, abstract things, for the clear benefit of the public.
And this whole idea, it goes way back, doesn't it? It's not just a modern thing.
Oh, incredibly deep historical roots. It really tracks alongside human technical progress. Think back to the 15th century, Gutenberg and his movable type.
Right, revolutionary.
Totally. But it still took centuries, until around 1850, for the sizes of the type itself to become properly standardized internationally.
So before that, if I ordered, say, a 12-point font from two different places,
they might not match up. Standardization just made everything simpler: communication, trade, the whole print industry.
Makes sense.
And it applies to physical stuff too, obviously. Just 25 years after that printing standard, 1875, 17 countries signed the International Meter Convention.
Finally making the meter everywhere.
Exactly. A universally accepted, valid unit. Huge for global trade, for science, for everything. Predictability.
So today, standardization works on, three main levels? How do they fit together?
Okay, so globally, you've got ISO, that's the International Organization for Standardization, and IEC, the International Electrotechnical Commission. They aim for worldwide consensus.
Got it. Global first.
Then you zoom in to the European level, that's CEN and CELEC. Their focus is harmonization, making sure standards align across Europe to help the single market work smoothly.
Okay, Europe level.
And finally, you have the national level, like DIN in Germany. Often, national bodies like DIN will adopt the European norms, the EN standards, but they apply them specifically within the country, sometimes with national additions.
Right. And here's the key bit, the thing everyone involved in building needs to really get. These norms, these standards.
Yeah.
They aren't automatically laws.
That is absolutely the crucial distinction. Fundamentally, norms are recommendations. Using them is voluntary.
Voluntary, but surely.
They only become legally binding in basically three situations. First, if you agree to follow them in a contract, like in a construction bid.
Okay, contractual agreement.
Second, if a law or a building regulation specifically points to that norm and says you must follow this.
Referenced in law. Makes sense.
And third, if the norm describes a sort of essential property of a product that's needed just to sell it in the market, like a basic safety requirement.
But in practice, especially with something like fire protection, sticking to DIN and EN norms is pretty much essential, right?
Right.
Because they represent the accepted state of the art.
Absolutely. If you decide to not follow a standard, say a specific DIN requirement, you're taking on a massive burden. You have to prove beyond any doubt that your alternative method provides an equivalent level of safety. Equivalente Sicherheit.
And most people aren't going to risk that liability.
Exactly. Most professionals just won't take that chance. It's far easier and safer to stick to the established, recognized standards.
Okay, that sets the stage really well. With that foundation laid, let's get into our first main segment. We need to talk about fire itself, this, ancient force, starting with Chapter 1 in the source, the origin of fire.
Yeah, the human relationship with fire. It's one of the biggest steps in our evolution, isn't it? Learning to control it wasn't just about staying warm. It was the first major move towards actually mastering the environment.
And initially, Humans probably just found fire, right? From lightning or something.
That's the thinking. Early humans likely secured naturally occurring fires first. Then came the challenge, keeping it going. That required conscious effort, planning ahead. For cooking, for protection.
And the archaeology is showing the effort just to keep fire going even before they could reliably make it. That's amazing. We have to talk about Ötzi.
Ötzi the Iceman. He's a perfect snapshot of advanced fire preservation from about 5,300 years ago.
What do they find?
He was carrying a container made of birch bark. Inside, packed carefully in fresh leaves to insulate it, were glowing embers, charcoal.
Wow. So he could carry the heat, basically.
Precisely. He could transport the potential to make fire quickly, without the hassle of starting from scratch every time. That shows a really sophisticated understanding of how to manage combustion, keep it slow burning.
Like a primitive thermos for fire.
Kinda, yeah. But what's maybe even more revealing is what else he had, or rather what suggests he'd lost something critical. In his pouch, they found this black stuff.
Yeah.
Identified as trauma of foams fomentarius, that's true tinder fungus. It's known for catching even a tiny spark. And he had some flakes of pyrite or marcasite.
Okay, so tinder and pyrite flakes. Sounds like part of a fire starting kit.
Exactly. Part of one. The flakes, if you strike them against a proper fire strike stone, which he was missing, would create sparks.
Ah, so he was missing the stone.
Right. The fact he needed to carry those delicate embers suggests he'd lost his strike stone, meaning he couldn't reliably make fire anymore. He had to fall back on the much riskier strategy of just keeping it going. It shows both incredible knowledge and, likely, a recent critical equipment failure.
Fascinating. Okay, let's jump forward thousands of years. Fire goes from being this essential tool to, well, the enemy of the city. Ancient Rome is the classic example, right?
Oh, Rome was a tinderbox. Buildings packed tightly together, lots of timber, multi-story tenements. And people used open fires inside for cooking, heating.
So if a fire started.
It spread fast. Getting water from the public wells took time, and often it was just too late. Fires could wipe out huge areas.
Which leads us to the Great Fire of Rome, 64 AD, often blamed on Emperor Nero, but probably accidental.
Most historians think it was likely accidental, yeah. But the sheer scale of it forced Nero's hand. It led to one of the world's first real comprehensive urban fire codes, a Branded Nung.
He didn't just rebuild, he actually tried to prevent it happening again.
Exactly. He completely restructured parts of the city. His rules are quite forward-thinking for the time.
What sort of things did he mandate?
Wider streets to act as fire breaks, limits on how high buildings could be. And crucially, he pushed for construction using less flammable materials, like stone.
Okay, that sounds sensible.
But maybe the most important structural change was requiring walls that didn't touch, separating buildings with courtyards or open space that directly tackled how fire leaped from one timber building to the next.
That basic idea, fire breaks, separation, it's still fundamental to modern codes, isn't it?
Absolutely. It underpins everything.
Yeah.
Now, shifting to our times, Chapter 1 also looks at the terrifying scale of modern fire disasters, the huge wildfires.
Yeah, we see these devastating examples. Yosemite in 2013, started by an illegal campfire, burned for months. Or Black Saturday in Australia back in 2009. These aren't just natural disasters anymore, are they?
Not entirely. The source material points to a dangerous mix. Extreme weather, definitely droughts, high winds, climate change impacts, but also administrative failures.
Like what?
Well, in the U.S., for instance, the book mentions massive funding cuts in forestry, laying off something like 70,000 rangers. That drastically cut down on surveillance, on proactive forest management, the stuff that used to keep smaller fires from becoming mega fires.
The scale is just mind-boggling. That 2002 U.S. fire season destroyed 1.5 million hectares. Double the previous records.
It's a lack of preventative work, controlled burns, proper thinning combined with the hotter, drier conditions. When a fire starts now, it can just explode.
Okay, let's bring it back from the wilderness to inside our homes.
Yeah.
The main causes of fires in buildings are totally different, right? It's not usually lightning hitting the stove.
No, not usually. Domestically, the #1 cause. Technical defects.
Really?
Yeah, accounts for almost a third of house fires. Faulty wiring, dodgy appliances, damaged cables, short circuits, that kind of thing.
And after technical faults.
Then you get open flames, leaving candles unattended is a big one. And just simple human error, forgetting the iron is on, falling asleep while smoking, the usual suspects.
Okay, so if technical defects are #1, that perfectly sets up why. Chapter 8 on the Roquefort and Milder, the smoke alarm, is so critical. It's the absolute front line for safety at home. Why is detection the key?
It's purely about survival time, and it comes down to the smoke, not the flames initially. Get this. 90% of people who die in fires die from inhaling toxic smoke.
90%, wow.
And here's the truly scary part. 70% of those deaths happen at night while people are asleep. The toxic gases like carbon monoxide, they overcome you silently. You don't wake up.
That's terrifying. And it explains why basically all German states now have mandatory smoke alarm laws, like the Baby Art 46 you mentioned. Where do they absolutely have to be installed?
The rules are pretty standard now. Every bedroom, definitely, every children's room, and any hallway or corridor that's part of an escape route from living areas.
And this applies to old buildings too, not just new ones.
Yes, absolutely. There were staggered deadlines for retrofitting existing buildings. Often any major renovation triggers the requirement too.
Okay, now the tricky part. Who's responsible for making sure they actually work? The maintenance. That seems to be a legal headache.
Oh, it's a huge gray area and really controversial.
Yeah.
Generally, the landlord or the owner is responsible for putting the alarm in, the installation.
Right.
But the responsibility for keeping it working, checking the battery, testing it, cleaning dust off it, that often falls to the tenant.
Unless
the owner specifically takes over that responsibility. They can do that, but then they can usually pass the maintenance costs onto the tenant through the service charges. It varies state by state, and it causes a lot of confusion and arguments.
And the technology itself, the type of detector matters too, doesn't it?
It does. The most common ones you see now are optical alarms, type A. They work using scattered light smoke particles enter the chamber and reflect a light beam onto a sensor. The older type, less common now, are ionization alarms, type B. They use a tiny amount of radioactive material to ionize air, and smoke disrupts that current. But because of the radioactive element, they're often restricted in Germany, need special permits, proper disposal. Optical is pretty much standard for homes.
But regardless of the type, the real issue is time, right? How quickly does a small fire become unsurvivable?
Frighteningly quickly. The time between an alarm sounding and conditions becoming lethal, what they call flashover, where the whole room just erupts in flames, can be incredibly short. Sometimes just 1 to 3 minutes.
1 to 3 minutes.
Yeah. So you need alarms that detect reliably and quickly, but without constantly going off falsely. That's the balance.
Which brings us neatly to that legal case the sources mentioned about false alarms and who pays. The homeowner in Schleswig.
Ah, yes, that case. It really highlights the problem. A homeowner got hit with a bill for nearly 900 euros, 894 to be exact.
Why?
Because their standard, legally required smoke alarm went off falsely. It triggered a full fire brigade response. 5 vehicles, 20 firefighters turned up.
Wait a minute. The law makes you give the alarm. It goes off, maybe because of cooking steam or dust. And then you get penalized nearly 1,000 euros for complying with the law.
That's the crux of it. That's the moral and legal bind. The legal fight was basically about, is a simple mandatory domestic smoke alarm the same thing as a complex professional Brandmeldeanlage, a fire alarm system in a commercial building? Because those do often trigger call-out fees under local rules if they cause false alarms.
So if there had been a tiny bit of actual smoke, maybe smoldering pan, and they put it out, the call would have been free.
Pretty much, yeah.
But because the device worked as designed, detected something, even if it wasn't a real fire, and alerted the professionals, the homeowner pays.
Exactly. And you can see the problem. Local councils, especially volunteer fire departments, need to recover costs for unnecessary callouts from faulty systems. But applying that same logic to a mandatory, cheap consumer device, when false alarms are so common from everyday things,
it basically discourages people from trusting their alarms or makes them hesitate to call 911 if it goes off.
Precisely. It creates a massive financial disincentive and undermines the public acceptance of a vital safety measure. It's a tension that's still not really resolved. ### segment 2.
Wow, that 894 bill is a stark reminder. Safety isn't free, is it? Whether it's the gear or the potential liability. Okay, let's shift gears. We've talked about the first warning, the detection. Now let's move to the last line of defense.
Yeah.
The actual structure of the building. We're diving into the engineering, the materials, the reality versus the plan, starting with Chapter 2.
Right. Structural fire protection, it really rests on 2 main pillars. First, how the materials themselves behave in a fire. Do they burn, melt, release toxic fumes? And second, the fire resistance of the building components, walls, floors, beams. That's the foyer wider stand.
Like an F90 rating on a wall means it holds for 90 minutes.
Exactly. And we always have to remember fire protection isn't just about stopping flames. It's equally about stopping the spread of deadly smoke. It's always a dual goal, fire and smoke.
To really understand the stakes here, we almost have to look at a major failure, one that tragically reshaped how we think about modern buildings. The World Trade Center. Built in the 70s, its collapse showed the limits of the codes back then.
The WTC towers, built between 1970 and 77, they were engineering icons, designed to withstand the impact of a Boeing 707, which was a common plane at the time. But the impacts on 9/11 were from much heavier 767s, and they hit in a way that exposed some critical vulnerabilities in the design and materials.
And the sources point to a specific issue with the central core, the part with the stairs and elevators.
Yes, that central core. It was constructed using something called gipsbeton, gypsum concrete.
What is that?
It's a relatively lightweight material, often used for non-load-bearing interior walls. It was chosen partly to speed up construction and reduce the overall weight on the foundations.
Not reinforced concrete, then.
No. And the post-9/11 investigations suggested that if the core had been built with heavy reinforced concrete, the structural integrity, and therefore the time people had to evacuate, likely would have been significantly longer.
So the impact was devastating, but the fire was the real killer for the structure.
Absolutely. The planes hit critical zones: South Tower between floors 87 and 93, North Tower between 96 and 103, and each plane dumped around 3,800 liters of jet fuel. That ignited instantly, creating this incredibly intense fire, with temperatures estimated between 1,000 and 2,000 degrees Celsius.
And steel. We think of it as strong, but it doesn't like heat, does it?
Not those temperatures. Steel uses about half its strength at just 500 degrees C. In that inferno, fed by jet fuel, the steel columns and the floor trusses started to soften, warp, and then fail.
Even though the original design had a fire rating.
Yeah, the outer columns and beams were rated for F180 3 hours. But the North Tower collapsed in 103 minutes, and the South Tower went down in just 53 minutes. The combination of the impact damage and the intense heat overwhelming the structure, especially that less robust core, was just too much.
Such a rapid collapse. How does that compare to, say, a modern high-rise built with fire safety front and center?
Right.
Like the Commerzbank Tower in Frankfurt.
That's a great comparison. The Commerzbank Tower, finished in 97, also uses a steel frame, but it was designed for F120, 2 hours of resistance. The key difference is how they protect the steel.
How so?
All the critical steel structural parts are encased in fire-resistant boards, fiber-silicate platen, fiber-silicate panels. These boards act like insulation, keeping the temperature of the steel core below that critical 500 degrees C point for the full 2 hours. It dramatically slows down the weakening process.
So you protect the protector, basically.
Yeah.
Okay, if the big structural parts are the bones, we need to talk about the joints, the weak spots.
Yeah.
Chapter 2.14 looks at penetrations and sealing them, the Brandschutzfibel, the fire stops.
Ugh, fire stops. This is where so many projects fall down. They're absolutely essential anywhere. Services, cables, pipes, ventilation ducts have to pass through a fire-rated wall or floor.
Because otherwise you've just created a highway for fire and smoke.
Exactly. The seal itself has to match the rating of the barrier it's in. If it's an F90 wall, the penetration seal needs an R90 rating. The R stands for resistance, meaning it maintains its integrity and insulation for 90 minutes.
Seems simple enough in theory, but you're saying these get missed all the time. What are the common ways to seal these gaps properly?
There are a few main types of solutions. First, you have intumescent materials. These are foams, putties, caulks, even tapes that react to heat. They swell up dramatically, sometimes 10, 20 times their original volume, and choke off the opening.
Okay, they expand to fill the gap. What else?
Then you have fire stop plugs or stones. These are like pre-made rigid blocks or cylinders, often made of mineral wool or similar fire-resistant material. They're great for smaller circular holes, like where pipes or conduits go through, maybe 55 to 240 millimeters in diameter.
And they're easier to deal with if you need to add more cables later.
Exactly. They're good for installations that might change often, especially where you have a mix of things going through maybe some electrical lines next to non-combustible water pipes.
Right. But what about pipes that can burn? Like plastic pipes for water or waste?
Ah, good question. For combustible pipes, things made from B1 or B2 plastics, you need something different. You use pipe collars, Rohrmanschetten.
Collars.
Yeah, it's a metal collar that fits around the plastic pipe where it passes through the wall. Inside the collar is that intumescent material again. When a fire heats it up, the intumescent swells inwards, crushes the softening plastic pipe, and completely seals the hole. They can maintain an R90 rating for pipes up to maybe 300 or 400 millimeters.
Clever. Okay, before we leave materials, we have to touch on a really difficult legacy. Chapter 2.16, asbestos. The supposed miracle material.
Yeah, asbestos. The name itself comes from Greek, meaning everlasting or inextinguishable, and for fire protection, its properties were amazing. It doesn't burn. It only melts way up at 1,000 degrees C. It resists chemicals. It insulates incredibly well. It was used everywhere.
But the danger wasn't chemical, it's physical, right? The fibers.
Exactly. The hazard is its structure. It's made of these incredibly fine needle-like fibers. If the material gets disturbed during demolition, renovation, even just aging, these microscopic fibers get released into the air.
And you breathe them in.
Right. And because they're sharp and incredibly durable, they lodge deep in the lungs. They can pierce cells, cause inflammation, scarring,
Yeah.
leading years or even decades later to diseases like asbestosis, lung cancer, mesothelioma, really nasty stuff.
And even though it was banned or heavily restricted, starting around 1991 in Germany and then more widely, the problem hasn't gone away.
Not at all. Because it was used in so many products, estimates are over 300 different applications. Fireproofing spray on steel beams, insulation boards, ceiling tiles, floor tiles, gaskets, even in some old fire stops for cables.
So any work on older buildings is potentially hazardous.
Hugely. Demolition, renovation, even just routine maintenance in buildings from before the mid-'80s, especially industrial or public buildings, you have to assume asbestos might be present. It requires highly specialized regulated procedures for handling and removal to protect workers and occupants. It's a massive ongoing challenge.
Okay, let's move to a more modern material dilemma. Chapter 3 talks about thermal insulation composite systems, WDDS. This puts energy efficiency against fire safety.
It really does. WDBS systems are key to hitting energy goals, reducing CO2 emissions, saving on heating fuel, moving away from fossil fuels. They wrap the building in insulation. But the most common insulation used is often expanded polystyrene, EPS, or extruded polystyrene, XPS.
Which is basically plastic foam,
Yeah.
styrofoam.
Right. And plastic foam burns readily. It's classified as highly flammable.
And the problem isn't just that it burns, but how it burns on a building facade.
Exactly. Two big problems. First, it can allow fire to spread incredibly rapidly up the outside of the building, sometimes skipping multiple floors in minutes. We've seen horrific examples internationally, like the Grenfell Tower fire in London, where the cladding system contributed massively to the speed and scale of the disaster.
And the second problem.
Smoke. Burning polystyrene produces huge volumes of thick, black, toxic smoke, which makes escape and rescue incredibly difficult.
So how do regulations try to manage this risk? We still use these systems for energy efficiency.
They've become much stricter. For a system using EPS or XPS to be approved now, it has to include specific fire safety measures. The main one is incorporating brand-regal fire barriers or fire breaks.
What are those?
They are horizontal strips, sometimes vertical too, made of non-combustible material, usually mineral wool. They're installed at intervals within the polystyrene layer, like around window openings and between floors. They act to break the continuity of the flammable insulation, slowing or stopping the vertical spread of flames up the facade.
So it's not just a solid sheet of polystyrene anymore.
No, an approved WDVS system is much more complex than just the insulation board. It includes these fire breaks, special fixings, specific render coatings, and the whole system has to pass rigorous fire tests, like the EDIN 410220 standard, to prove it limits flame spread adequately. #tag segment 3.
Okay, we've covered the building's passive defenses, the structure, the materials. Now let's get into the active systems, the things designed to actually do something when a fire starts. Segment 3 kicks off with Chapter 17 on brand alarm systems, BMAs.
Right, the BMA. Its main job is simple. Early detection. The faster you know there's a fire and the faster that alarm gets to the right people, occupants, emergency services, the better the chances of saving lives and property. The whole system's value hinges on reliable detection.
Let's break down the components. How can these systems be activated?
Two main ways. Manually or automatically. Manual activation uses those hand fire alarm devices, the little red boxes on the wall.
Break glass things?
Usually, yeah, or sometimes a push button now. They have to be clearly visible, usually red, RAL 3000 red specifically. And if hitting that button sends a signal directly to the fire department, it has to be clearly labeled Feuerwehr.
And there are rules about where they have to be.
Yes, crucially, you shouldn't have to travel more than 50 meters from any point in the building to reach one. They need to be accessible on escape routes.
Okay, that's manual.
Mm.
What about the automatic detectors? How do designers choose which type to use where?
That's a critical design decision. You need to consider a few things. What's a room used for? A dusty warehouse is different from a clean server room or a kitchen that might have steam.
Right.
What kind of fire is most likely to start there? Will it be slow and smoldering, producing smoke first, or a fast flaming fire generating heat quickly? Room height matters too, as does the potential for environmental factors that could trick a detector, like dust, fumes, or high air velocity.
So based on that, you choose.
You might choose standard point smoke detectors, optical or ionization, though optical is more common now. Or maybe heat detectors if smoke detection is unreliable due to the environment. For large open areas like atriums or warehouses, you might use linear beam smoke detectors.
Hmm.
And in special cases, like where flammable liquids could ignite instantly, you might need flame detectors.
Now, big issue with these complex systems is false alarms. You mentioned the domestic rate earlier, but for these professional BMAs, it's a significant problem, right?
Oh, yeah. Estimates are that somewhere between 12 and 15% of all fire brigade callouts are triggered by false alarms from BMAs.
That's huge. Wastes time, resources, puts crews at risk.
Absolutely. So to combat this, BMAs can be set up to operate in different modes using technical tricks to try and verify if an alarm is real before calling out the fire brigade.
Okay, let's get into those modes. You mentioned OM, TM, and PM. What's OM?
OM is just the standard operating mode. One detector goes into alarm, the signal goes straight out. Simple, immediate response, good for high-risk places where you can't afford any delay.
Got it. What about TM technical measures?
TM uses the system's technology to filter out false alarms. There are a few ways. One common one is two detector dependency,
Meaning?
meaning you might need two separate detectors in the same area to both go into alarm within a certain time window before the system confirms it's real and sends the external signal. A single faulty detector or a brief local disturbance affecting just one won't trigger a full call-out.
Smart. Any other TM examples?
Yeah, another is verification logic. The system detects an alarm condition but waits, say, 10 or 20 seconds to see if it persists. If it clears quickly, maybe just a puff of dust, no alarm is sent. Or you can use more sophisticated multi-sensor detectors. These look at several things at once: smoke density, rate of temperature rise, maybe carbon monoxide levels, and use an algorithm to decide if it's really a fire or just, say, someone vaping nearby.
Okay, that makes sense. What about the last one? PM personnel measures.
PM is different because it involves people. It's only allowed if you have trained staff present on site 24/7, or at least during operating hours.
And what do they do?
In PM mode, when an alarm activates, the signal first goes to an internal control panel or monitoring station on site. The transmission to the fire department is deliberately delayed for a short period. This gives the on-site staff time to check their systems, maybe look at CCTV, or even quickly go investigate the location.
And if they see it's a false alarm, maybe someone hit a manual call point by accident.
They can cancel the external alarm before it ever goes out to the fire brigade. Saves a needless deployment. But if they confirm it's real, or if the delay time runs out, the alarm goes straight to the fire service. It requires reliable staff and clear procedures.
Okay, that covers detection and alarming. Let's move to actually fighting the fire. Chapter 19, sprinkler systems. The controlled rain. What's their main goal?
Sprinklers have a very specific job. Detect a fire early and then control it, suppress it, or ideally extinguish it completely while it's still small. The idea is to keep things in check, protect escape routes, and limit damage until the professionals, the fire service, arrive to take over fully.
And there are different types depending on whether the pipes have water in them all the time.
Exactly. The most common type is a wet pipe system. The pipes are always filled with water under pressure. When a sprinkler head activates, water sprays immediately. Simple, fast.
But you need to worry about freezing in cold areas.
Absolutely. Frost protection is critical for wet systems in unheated spaces. That's where dry pipe systems come in. The pipes are filled with compressed air or nitrogen. When a sprinkler head opens, the air rushes out, a valve opens, and then water flows into the pipes and out the head. Slower response, but no freezing risk.
Okay, and there's a third type, pre-action.
Yeah, pre-action systems are a bit more complex, often used where accidental water discharge would be disastrous, like in a computer room or archive. They usually require two things to happen before water enters the pipes. First, a separate fire detection system, like smoke detectors, has to activate, and then a sprinkler head also has to operate. It's a belt and braces approach against accidental flooding.
Got it. Now, designing these systems depends heavily on the fire risk, right? You mentioned the VDS CEA 4001 classification. How does that work?
Yes, that classification is fundamental. It categorizes the hazard level of the area being protected. You have LH light hazard. Think small offices, schools, hospitals, rooms, areas with low amounts of combustible material where a fire isn't expected to grow quickly.
Okay, LH is low risk.
Then OH, ordinary hazard. This is the middle ground, covering most commercial and light industrial spaces, car parks, restaurants. It's further subdivided based on the specific type of risk.
And the highest level.
That's HHP or HHS, high hazard process or high hazard storage. This is for places with serious fire, potential chemical plants, warehouses with high piled storage of flammable goods, places where fire could spread very rapidly and intensely.
Why is this classification so vital?
Because it dictates everything about the sprinkler system design. How much water needs to flow, the density, how far apart the sprinkler heads can be, the size of the pipes needed, and critically, how many sprinklers are expected to operate simultaneously in a worst-case fire scenario for that specific hazard. A high-hazard area needs a much more robust system than a light hazard area.
And a source gave that interesting example about storage. How the same material can be different risk categories just based on how it's stacked.
Right, the bituminous felt example. If rolls of roofing felt are stored lying flat, they pack densely, less air circulation, it's maybe a Category 2 storage risk.
Okay.
But if you stand those same rolls up on end, you create taller stacks, more air gaps, potential for fire to spread vertically much faster, suddenly it jumps to a higher risk, Category 3, demanding more water from the sprinklers. It shows how nuanced risk assessment has to be.
Absolutely. Now, none of this works without water. A reliable supply is non-negotiable.
Totally useless without it. You need a guaranteed source with sufficient volume and pressure. That usually means large water storage tanks on site, maybe elevated tanks for gravity feed, or powerful pump sets drawing from the town mains, or a dedicated reservoir.
And the pumps themselves need careful design.
Yes, especially ensuring they have reliable power. And a key point from the source is keeping the sprinkler pumps separate from the pumps supplying fire hydrants, unless you have a specifically designed combined system that can handle both demands without failing. You don't want the sprinklers running out of water because the hydrants are being used heavily.
Okay, now the source mentioned something intriguing, nitinol, the nickel-titanium-shaped memory alloy from 1962. Used in glasses frames, apparently. How does that relate to sprinklers?
Nitinol. It's famous for its shape memory effect. You deform it, then heat it past a certain point, and it snaps back to its original shape. The source mentions its common uses, but implies relevance to sprinklers.
So how? Most sprinklers use that little glass bulb filled with liquid, right?
That's the most common trigger now, yes. The liquid expands when heated, shatters the bulb at a precise temperature, and releases the water seal. Before glass bulbs, and still in some specialized heads, they used a fusible link.
Fusible link.
Yeah, basically two pieces of metal held together by a solder designed to melt at a specific temperature. When the solder melts, the link separates, opening the sprinkler.
So could nitinol be used instead of solder?
That's the likely connection. You could potentially design a sprinkler activation mechanism using a nitinol element. When the ambient temperature hits its transition point, the alloy changes shape rapidly and forcefully, providing a very reliable quick response release mechanism. It might be used in specialized fast response sprinklers, leveraging that predictable temperature-triggered physical change. It's an example of advanced material science finding its way into these critical safety devices.
Interesting. Before we leave sprinklers, what are the main things that can go wrong with maintenance? What needs checking?
Maintenance is everything for sprinklers. For wet systems, ensuring the frost protection works is vital. Corrosion inside pipes is a huge enemy, potentially blocking flow or causing leaks. Regular inspection, maybe internal checks.
And the heads themselves.
Critically important. The activating element, the glass bulb or fusible link, must be kept clean. If sprinkler heads get covered in dust, grease, or worse, get painted over during renovations.
It insulates them.
Exactly. It delays activation because the heat can't get to the element efficiently. A painted sprinkler head might activate too late, or not at all. They absolutely must be cleaned carefully or replaced if contaminated. It's a common but dangerous oversight.
Okay, one more active system before we move on. Chapter 27 introduces smoke protection pressure systems, RDAs. These sound specialized.
They are highly specialized, yes. RDAs, or Rauchschutzanlagen, are all about controlling smoke, specifically in escape routes.
How do they work?
Their goal is to keep critical areas, primarily stairwells, totally free of smoke during a fire. They do this by pumping fresh air into the stairwell, creating a slightly higher air pressure inside than on the fire floors.
Positive pressure.
Right. This positive pressure physically pushes back against smoke, heat, and fire gases, preventing them from flowing into the protected stairwell when a door is open from a fire floor. It keeps the escape route clear and usable.
Where are these essential?
They're typically required in enclosed stairwells that serve taller buildings, usually over 22 meters high. Also in designated safety stairwells, which are built to a higher standard of fire resistance, and in the lobbies and shafts of dedicated fire service elevators. They ensure these vital routes stay tenable for evacuation and for firefighters going in.
Given their life safety role, the reliability must be paramount. Power supply, for instance.
Extremely high standards. The fans need a very secure power source. That means connection to a dedicated emergency power grid, an SV nets, or having redundant backup from batteries or a diesel generator, all meeting strict standards like ISO 8528.
And maintenance.
Equally stringent. Because they are so critical, RDA systems must undergo thorough inspection and functional testing by certified specialist experts every single year. You can't skimp on maintaining the system that guarantees your escape route stays clear. Hashtag tag segment 4. Okay, we've covered a lot. Detection, structure, active suppression. This final segment, segment 4, really gets into the messy human side of things, where errors happen, where coordination breaks down, where liability comes into play, and where maybe the system still falls short. We start with Chapter 4, accountability and oversight.
Yeah, this is where the best laid plans can fall apart. When things go wrong in fire protection, the errors often trace back to specific phases of the project. You see typical mistakes in planning, execution, and monitoring.
Give us some examples from the planning stage.
A classic planning error is designing escape routes that are too long, exceeding the maximum permitted travel distance to safety. Or maybe specifying the second escape route, often relying on fire brigade ladders for a window that the ladder physically can't reach due to obstructions or ground conditions. Simple oversight, but potentially fatal.
And then execution errors, the mistakes made on the actual building site.
Oh, plenty of those. Installing fire stops those brand shots we talked about incorrectly, leaving gaps or using the wrong type. Putting in a fire door but forgetting the crucial smoke seals around the edge.
Or building a firewall that doesn't quite connect properly.
Exactly. Stopping a fire-rated wall just below the suspended ceiling instead of running it all the way up to the solid structural slab above. That creates a hidden path for fire and smoke to just bypass the barrier completely through the ceiling void. A really common, dangerous mistake.
And monitoring errors. That sound like quality control failures.
It is. It's about making sure what's actually installed matches what was specified and approved. A common monitoring failure is contractors substituting materials, maybe using cheaper cables that aren't halogen-free, when the fire concept specifically required them to minimize toxic smoke.
Or even just installing something backwards.
Yes. Like mounting a fire door so it swings into the escape path instead of outwards. In a panic, people pushing against it could create a deadly bottleneck. Simple installation error, huge consequences.
Now, when these kinds of failures happen, not just individually, but systemically, across a huge project, you get chaos. The source uses the Berlin Airport BER as the prime example of this organizational meltdown.
BER is the case study, isn't it? Because the intention was actually really good. After the terrible Düsseldorf airport fire in 1996, the fire protection concept for BER was meant to be absolutely state-of-the-art, incorporate all the lessons learned.
So what went wrong?
It was too complex. The planners relied heavily on complicated engineering calculations and alternative solutions to prove equivalent safety instead of sticking to simpler prescriptive rules from the standard building codes.
And that complexity created bureaucracy.
Massive bureaucracy. Every little deviation from the norm, every modification during construction required complex reassessment and approval. The approval processes just couldn't keep up. The whole system became gridlocked, essentially non-functional because changes were happening faster than they could be validated. Construction ground to a halt for years.
Which led to that utterly bizarre proposed fix.
The man-machine solution. It sounds like something out of a dystopian movie. They seriously propose hiring hundreds, maybe thousands of people to sit watching monitors 247. If an alarm went off, these people would physically run to the location and manually close fire doors or operate smoke vents because the automated system couldn't be relied upon.
Unbelievable. Did that actually happen?
Thankfully, no. The building authorities vetoed it. They recognized it was completely unworkable and no substitute for a properly functioning automated system.
It sounds like when the original lead planners were fired, the whole project just lost its way.
That seems to be the consensus around 2012. Removing the core planning team meant there was no single coherent vision or authority left driving the fire safety integration. The source quotes someone saying, essentially, No one had a plan anymore.
Chaos.
Complete chaos. Without clear direction, subcontractors came in, did their bit, often installing things that didn't meet the already complex and changing requirements. It resulted in tens of thousands of documented fire safety defects that took years and hundreds of millions of euros to identify and fix later.
So the big lesson isn't just about fire safety tech, it's about project management.
Absolutely. The critical takeaway is that complex projects need a clear, single point of leadership and an integrated structure. As one observer put it starkly, the project manager should not be a four-person team. BER suffered from a catastrophic failure at the interfaces between different systems and responsibilities.
Which underscores why that formal fire protection concept, the branches concept, Chapter 13, isn't just paperwork. It's the essential roadmap.
It really is. For any non-standard building, the concept is the key document. It has to outline the specific protection goals, define the assumptions, justify the measures being taken, especially if they deviate from standard code. It's the basis for approval by the authorities.
And it's legally required for certain building types.
Yes, especially for what are called Sonderbauten special buildings. Things like high-rises, hospitals, large shopping centers, assembly halls, big garages. For these, a certified expert often needs to create and vouch for the concept, and independent checks during construction are usually mandatory.
And this is where you formally justify any deviations from the standard code.
Exactly. If you can't meet a specific rule in the building code, the concept is where you present your engineered alternative solution and argue that it provides an equivalent level of safety. It provides both the technical plan and the legal basis for the project's fire safety design.
Okay, let's shift now to what the sources identify as perhaps the most critical and maybe ethically troubling unresolved issue. Chapters 12 and 26 touch on the accessibility crisis in evacuations.
This is a really stark point in the material. We design escape routes the first rescue path to be usable, smoke-free for a certain time. But the codes consistently struggle with, or arguably fail, the people most vulnerable in a fire. Those who are officially deemed not capable of self-rescue.
Who falls into that category?
It's a broad group. People with mobility impairments, wheelchair users, people with sensory disabilities, blind or deaf, the very elderly, people who are bedridden, even parents trying to evacuate with infants or very young children.
And the main accessibility standard, DIN 18040. How does it handle their evacuation?
This is where the sources point out a major contradiction, even a danger. The standard identifies this group as needing assistance, but then essentially punts the responsibility. It says their evacuation needs should be addressed in the building's specific fire protection concept, which then gets submitted to the local fire department for approval.
So it's not standardized, it's case by case, and relies on local fire departments to evaluate these specific plans.
Pretty much. And the source is quite critical, calling this a potential life-threatening security loophole. Because in reality, for someone in a wheelchair on the 10th floor when the elevator shut down in a fire, what is the plan? Relying on firefighters to carry them down multiple flights of stairs, it's often impractical and takes too long. Every staircase becomes a trap.
This must be an even more acute problem in places like hospitals, covered in Chapter 26.
Exactly. In hospitals, the majority of occupants cannot self-rescue. They're ill, injured, maybe unconscious, connected to equipment. Evacuation is incredibly complex.
So hospital fire safety design has to be different.
It has to prioritize two things. First, extreme compartmentation to slow fire and smoke spread, buying as much time as possible. And second, facilitating horizontal evacuation.
Moving people sideways, not downwards.
Yes. Designing adjacent fire compartments that act as safe refuge areas. So if there's a fire in one ward, staff can move patients across a fire barrier into the next safe ward on the same floor, rather than attempting a risky vertical evacuation downstairs. Secure fire separation for critical zones like operating theaters, ICUs, and IT rooms is also vital. But even with horizontal evacuation, the logistical challenge of moving potentially hundreds of non-ambulatory patients quickly and safely remains immense and arguably not fully solved by current codes.
It really highlights that gap. Okay, let's look at how some of these vulnerabilities get created in the first place. Chapter 24 talks about the coordination failures, the interface problem, the Schnittstellen problematic.
Ah, the interface problem. This is absolutely endemic in construction. It happens because building projects involve so many different specialist trades working in parallel, often in silos. You have the architects, structural engineers, electrical planners, HVAC, heating, ventilation, air conditioning installers, fire protection specialists, door installers.
And they don't always talk to each other effectively.
Or worse, they make assumptions about who is responsible for the bits where their work meets someone else's. They operate thinking, that's not my job, someone else will deal with it.
Can you give the classic example of how this plays out with fire safety?
The perfect example is those fire stops for penetrations again. The electrical consultant plans the cable routes through walls. They assume the architect or maybe the HVAC planner will specify how those holes get sealed. The HVAC planner runs their ducts, assuming the same thing. The architect might detail the wall construction, but assume the individual trades will seal their own penetrations according to code.
So because nobody was explicitly tasked and contracted to do the sealing.
It doesn't get done, or it gets done poorly by someone unqualified. That critical fire seal, the brand shot, falls into the gap between responsibilities. The fire compartment integrity is compromised purely due to a lack of coordination.
So what's the solution? How do you overcome these silos?
It requires a deliberate, integrated approach. Often, the recommendation is to establish a dedicated safety coordination role or even a roundtable safety commission on larger projects.
Bringing everyone together.
Yes, a body that integrates all the different safety aspects, fire protection, workplace safety, maybe environmental protection too. Its job is to force communication, identify these interface conflicts early, review plans collaboratively, and crucially, make sure that responsibility for every critical safety element, especially those interface points, is clearly assigned in the contracts. Someone has to own it.
Makes sense. Okay, finally, let's connect all this back to the real world of business and risk. Chapter 16 looks at fire insurance. What does the standard policy actually cover?
A typical fire insurance policy, like one based on the German AFB 2016 conditions, covers financial loss to insured property caused by a specific list of perils. That's usually fire itself, hostile fire, not a controlled one, lightning strike, explosion, and impact from an aircraft or things falling from it.
And it covers more than just the burnt items.
Yes. Importantly, it usually also covers consequential damage caused by the event or the efforts to fight it, things like water damage from extinguishing the fire, damage during necessary demolition, or clearing of debris afterwards.
Now, getting that insurance payout isn't automatic. It depends heavily on the policyholder being upfront about the risks.
Absolutely. When you apply for the insurance, you have a duty to disclose all circumstances you know about that are relevant to the risk the insurer is taking on. If you hide something significant, the insurer might later be able to refuse a claim or even void the policy entirely.
And that duty continues even after the policy starts.
Yes. You also have an ongoing obligation to notify the insurer immediately if the risk increases significantly during the policy term, a Gefahrerhome. For example, if you start storing flammable materials you didn't have before, even if that increase happens without your direct involvement, you still need to inform them. Transparency is key.
But there's a flip side to this risk assessment, isn't there? Insurers actually give discounts for good fire protection.
Oh, definitely. There are significant financial incentives, rebates, or rabat on the premium for implementing robust, certified fire safety measures. Insurers, especially those using VDS certification standards, recognize that good protection reduces their potential payout.
What kind of discounts are we talking about for, say, having a certified BMA system?
For a VDS-recognized automatic fire detection system, BMA, especially if the alarm signal goes reliably and directly to a permanently staffed monitoring station or an on-site fire service, you could see premium reductions of up to 20%.
20% is substantial. What about investing in people, having your own fire crew?
That yields even bigger rewards. Having a professionally trained, permanently staffed works fire service on site, your own immediate response team can earn the highest discounts for organizational measures, potentially up to 35% off the premium.
Wow. 35%.
Even having a recognized works fire service that isn't necessarily staffed 24/7 but meets certain standards can still get you maybe a 5% discount.
And the active extinguishing systems we talked about.
Sprinklers. Automatic extinguishing systems like VDS-certified sprinklers or maybe gas suppression systems in specific areas generally secure the largest discounts on the technical side, sometimes up to 50%.
Half-price insurance premium.
Potentially, yes, for that portion related to fire risk. Even having well-maintained manual systems like certified fire hoses and hydrants can still earn a decent discount, maybe around 25%. It clearly shows that investing in good fire protection often pays for itself through reduced insurance costs, not to mention the primary benefit of protecting lives and business continuity. Hashtag outro.
Okay, we have covered a huge amount of ground in the last, well, quite a while. From Otzi the Iceman, carefully carrying embers in birch bark,
To the complex, cascading failures at the Berlin airport.
and right through to the hard financial calculations of insurance premiums and safety discounts.
I think the main thread, the absolute key takeaway from all this source material, has to be that fire protection isn't just one thing. It has to be treated as that Gesamtwerk, a single, comprehensive, interlocking system.
Right, it's not just the fancy technology.
No, its success depends just as much on really rigorous, coordinated planning between all the different experts involved. It depends on meticulous execution on site, making absolutely sure every little penetration is properly sealed. And it depends on continuous disciplined vigilance when it comes to inspection and maintenance. You can't let things slide.
Okay, so here's the final thought, the provocative question that really emerges from digging into these sources. We've made incredible progress, haven't we? Sophisticated alarm systems, materials that resist fire for hours, sprinklers that react instantly, huge financial drivers for safety.
Huge progress, yes, but
But the sources relentlessly point to one major ongoing challenge. A moral challenge, a technical challenge, that still seems largely unresolved today.
and that has to be the systemic failure to guarantee truly barrier-free, safe self-rescue for everyone.
The accessibility gap.
Exactly. We engineer incredible systems to contain fire, to suppress it, but we still haven't fully cracked the structural and, frankly, the legal problem of creating genuinely usable, protected escape paths for those people the codes themselves define as not capable of self-rescue. The elderly, the disabled, people in hospital beds.
It's still a known vulnerability.
It's a known life-threatening security loophole, especially visible in high-risk places like hospitals and care homes. And according to this material, tackling that specific vulnerability ethically and technically is the single most critical area that demands our urgent attention going forward. You now know where the real unresolved danger still lies.